We're looking for the two missing angles, A and B. What's the relationship between those two angles here? They add up to 180. Perfect. A plus B equals 180 degrees. So then we have to just put in the expression 3x plus 7 plus the 5x plus 13 equals 180. So now to solve that, what do I do next? Well, before I can start solving it, I have to make sure I combine everything I can on each side. So on the left side, I have 3x and 5x, which make 8x. Then I have 7 and 13, which makes positive 20, so plus 20. Then I still have 180 on the right side. Now I have everything combined and simplified that I can start to solve it. What am I going to do first? Subtract the 20. So 8x equals 160, and then divide by 8. Perfect. So x equals 20. Now that doesn't answer the question yet. We still need to go back up here and find each of the angles. So 5x plus 13 will become 5 times 20 plus 13. 5 times 20 is 100. Plus 13 is 113. So this angle B is 113 degrees. The other one, angle A, is 3x plus 7, so that'll be 3 times 20 plus 7. 3 times 20 is 60, plus 7 is 67 degrees. Now just to make sure those add up to 180, and they do, so that's relatively sure that those are correct. Any questions on that one? Okay, so then moving over to number 2 over here, finding angles C and D. What's the relationship between those two angles? They have to be equal. C is equal to D. So when we put our expressions in, 5x minus 2 has to equal 3x plus 11. And now here it's a little bit different than we had before. The variable appears more than once, but this time it's on different sides of the equal sign. So over here I was able just to combine the 3x and the 5x to make 8x. Over here I have to approach it differently. I need to get rid of one of them, which is going to be the 3x, which is the smaller one, right? So we're going to subtract 3x. That'll be gone, leaving us with just 11 over there. I have to subtract 3x from the left side as well. I can only take that away from the 5x. So 5x minus 3x is 2x. We still have the negative 2 there. Now what? Well, I have to add 2 to both sides. So I have 2x equals 11 plus 2 is 13. And then divide by 2. X equals 6.5. Now again, we are not done. We need to go back up here and find the angles. So 5 times x becomes 5 times 6.5 minus 2. 5 times 6.5 is 32.5. Minus 2 is 30.5 degrees. Now we need to double check to make sure this other one turns out the same. 3 times 6.5 plus 11. 3 times 6.5 is 19.5. Plus 11 is 30.5 degrees. So they do come out to be the same. Both 30.5 degrees would be our answer. Any questions on those? Okay. I want you to try another one here. We have a valley here that is 7 feet deep on one side and 15 feet deep on the other side. And across it is 15 feet. I want to build a bridge to get across here. What is the minimum length of that bridge? I'm going to give you guys a couple minutes to think that over. Anybody want to throw out the answer they got for this? I heard somebody mumble it there. 17 feet. Let's take a look. This is actually just a right triangle problem. If we cut this across here, this makes a rectangle down here, so this has to be 7 feet. So what that means is this distance is just going to be the same as this one, 15 feet. And this distance here is going to be the 15 minus 7, or 8 feet. And there's the right angle of a right triangle. So x is just the hypotenuse of a right triangle. So I'll let a equal the 15 and b equal the 8. C is going to equal x. A squared plus b squared equals c squared. A is the 15, so 15 squared plus b is 8, so that's 8 squared, equals c is x, so that'd be x squared. 15 squared is 225. 8 squared is 64. 225 plus 64 is 289, equals x squared. So to solve that, it's x squared, so to get rid of the squared, we have to square root. Square root of 289 is 17. So that is 17 feet across. So we're going to look at a trapezoid here quick. Now a trapezoid has two sides that are parallel, the top and the bottom in this case. I'm going to tell you that the top up here is 15 inches. This side over here is going to be 10 inches. From here to here is going to be 6 inches. All the way across the bottom is going to be 36 inches. What I want you to try to find is this length here, this side right here. I want you to take a couple minutes and see what you can find from that. I see some of you still picking away at it, some of you giving up. Obviously, we're still doing right triangles here. So the first step is to find the right triangles. There are two right triangles in this problem. One right here, and the other over here. Well, to do anything with a right triangle, we have to know 2 out of the 3 sides. So that tells us we're going to be working over here where we have the 10 and the 6, and we can be finding this other missing side. I'm going to call that one of the legs, so I'm going to call it side A. The 6 here is going to be side B, and then of course 10 is the hypotenuse, so that'll be side C. So I'm going to start there finding A. A squared plus B squared will be is 6, so that's going to be 6 squared, equals C squared, so that's 10 squared. A squared isn't going to change. 6 squared is 36. 10 squared is 100. And now we're going to keep solving from there by subtracting 36. So we're left with A squared on the left. 100 minus 36 is 64. And now we're going to square root. So A squared square root is just A. Square root of 64 is 8. Technically 8 or negative 8, but negative 8 doesn't work for length. So that tells us that this here is 8 inches. Now, because we have a rectangle here, that means this here must also be 8 inches. If you look really close, and this is one of those skills that we're finding that is not as strong as it used to be. Finding missing dimensions like this. It's 36 inches all the way across. It's 6 inches from here to here. This distance from here to here must be the same as the 15 inches. So that's a total of 21 inches between those two measurements. Take that from the 36, makes this here 15 inches. So 6 plus 15 plus 15 has to add up to that 36. Now, we have this triangle here where we have the 8 and the 15. Those are both legs, so I'm going to call them sides A and B. Side C is the hypotenuse up there, which is x, what we're looking for. So A squared, A is 8, so it's going to be 8 squared plus B squared, well, B is 15, so that'd be 15 squared equals C squared, well, C is x, so that's going to be x squared. And now we'll just solve that. 8 squared is 64. 15 squared is 225. This is looking a little familiar. That adds together to be 289 equals x squared. And we square root. So 17 equals x. So this is 17 inches here. So last week we looked at this Pythagorean theorem, a squared plus b squared equals c squared. And we saw some of these basic applications, distance across a rectangular lawn or whatever. It can also be used in construction for squaring up a basement. If you have a basement that has certain dimensions, let's say, this is going to be 24 feet across here. Oh, let's come out to be. Oh, that ain't gonna work. Let's just say that's 24 feet across there, and this is going to be 40 feet across here. If I want to know how far it should be corner to corner, I can use this Pythagorean theorem. That'll be a right angle. This will be sides A and B. Doesn't matter which is which. The diagonal is side C. So it's 24 squared plus 40 squared equals C squared. And now we go ahead and solve it. So 24 squared is 576. We do 40 squared, which is 1600. We add those together, 576 plus 1600 is 2176 equals c squared. And now we go ahead and square root. So the square root of 2176 is 46.65. So C is 46.65 feet. If this were a construction-based class or architectural-based class, I would take the time here to go through and show you how do I take that decimal feet, 46.65, and turn it into something a little more useful like feet, inches, and either eighths or 16ths of an inch. That's not our purpose here, so I'm not going to do that. If anybody's really curious, let me know, and if we have time at the end of the hour, I'll show you. So anyway, that is some of the applications of that Pythagorean theorem, a squared plus b squared equals c squared. So continuing on with the geometry, the next step that we're going to take is we're going to look at circles. And we're going to look at some of the relationships within circles. To do that, we need to define some vocabulary first of all. A circle is actually completely defined by two features. One is its center, the location of its center. Pretend that's in the middle of the circle. And the second is the radius. And the radius is just the distance from the center of a circle to any point on that circle. Now, there are other lesser features of the circle that become important. A line segment that has its endpoints on the circle is called a chord. We're just doing a light geometry in this course, so we're not going to spend a lot of time working with chords. In a more, like I said, more geometry-based course, we would come back and spend a lot more time with that. And next we have a chord that actually contains the center of the circle, which is called the diameter. So the diameter has its endpoints on the circle, and it also contains the center of the circle. And so the first relationship we can find there is between the diameter and the radius. The diameter, which we're just going to represent with a small d, is 2 times the radius. If you think about it, the center to the outside is once on each side of that diameter. So if I have a circle with a radius of 7 inches, the diameter will be 2 times 7, or 14 inches. Now then, we have something called a circumference. The circumference is the distance around the circle. And to talk too much about the circumference, we need to, before we can talk too much about it, we have to define a constant called pi. And that's its symbol like that. It's the pi symbol, the Greek letter pi. It's sometimes written out pi, capital Pi like that. Pi is defined to be the ratio between the circumference and the diameter. So it's c for circumference divided by d for diameter. That equals pi. Well, pi actually goes on forever. Many of you have probably seen it before in different forms. Most commonly, we just approximate it with 3.14. And for most of my math lab, it's going to ask you to use 3.14. It's technically 3.141596, blah, blah, blah. I think there might be one problem on there where it actually is 3.1416 or something like that. Make sure as you're doing those problems, you check to see what they're asking you to use for pi. So if I have a circle with a diameter of 10 feet, the relationship between the circumference and the diameter is that the circumference is going to equal to the diameter times pi. I'm just solving this equation here for circumference by multiplying both sides by pi. So in this case, that circumference equals 10 times pi. 10 times 3.14 is going to be 31.4. That is in feet, because this was feet. Now you may have seen that the circumference is really what serves as the perimeter for a circle. And we've looked at perimeter on other shapes. For a rectangle, for instance, we came up with that formula. Perimeter is equal to 2 times the length plus 2 times the width. You're probably getting a little tired of seeing that one by now. We've seen it enough. But for any other shape, the perimeter can be found by simply adding up the sides. You know, for a simple triangle, I might have sides A, B, and C. The perimeter is just A plus B plus C. So the next step from talking about perimeter is to talk about areas. If we go back to last week when we started talking about geometry, we said everything starts from that point. From that point, we can move it in a single direction, and it creates a length. It's called a line segment, and the length is equal to the distance it moved. Well, we can now take that line segment, that length, and we can move it in a second direction, perpendicular to the first. And if you think of dragging a stick across the sand, it would trace out a rectangle. The width of that rectangle is also equal to a distance moved. And we had talked last week about we've moved in two directions. We've created distances in two directions. It is now a two-dimensional object. The area covered, the area is just equivalent to the space that is covered by the surface that is covered by that. And the amount of area, the size of that area, depends on the original length and the distance it was moved, that width. Now, it doesn't have to be a rectangle like that. If we think of one of the basic concepts in math, one of the basic tools in math is to slice things up into really thin rectangles when we find areas. So like here, we could slice this into really thin rectangles. Now, obviously, these aren't really thin because I'm drawing them thick enough that you can see them. What I'm talking is like thin, like sheets of paper stacked up to make that rectangle. The area of this end is, let's give it some numbers here. Let's say that this is 12 inches by 5 inches. So the area of that length of 12 inches times the width of 5 inches, 12 times 5 is 60. Remember, when we multiply, we also combine the names. So inches times inches are inches squared, or square inches. So it's 60 square inches. But what if those sheets of paper weren't stacked up straight? What if I stacked them off to the side a little bit? Kind of gave the top of the pile just a little bit of a shove. But you can tell this is still 12 inches across here, and this thickness isn't going to change. It's still going to be 5 inches. That area is still going to be the same. "12 inches by 5 inches, or 60 inches squared, square inches." But you'll notice the key here is when we find areas, we are multiplying two dimensions that are at right angles to each other. This 12 is the length. This 5 here is at a right angle. It's perpendicular to the 12. It is the distance to the other side of the figure. As we keep working with distances, we can run into triangles. Now, at first, we look at that triangle, and it might be easy to think that, well, that's not an area. That's not a length that's been moved in that second direction. But if we fill it in like this, we can see that that triangle is just half of a rectangle. So if I give this some dimensions here, let's say that this is still 5 inches, this is still 12 inches, the area of that triangle will be the 12 inches times the 5 inches. That's the area of the rectangle. We call that the related rectangle. The triangle is just half of that. We divide by 2. So 12 times 5 is 60. Divide by 2 is 30. It's still inches times inches is inches squared. So if I have 8 feet by 20 feet, recall those right angles there. So you know that's a rectangle. If I have what's called a parallelogram, there's 20 feet here. Now the 8 feet has to be given at a right angle across there. Or if I have a right triangle, that's 20 feet here and 8 feet here. Those are all related. The first two here, of course, the area is going to be 20 feet times 8 feet, just length times width, giving us 160 square feet. What's the area of the second shape going to be? It's the same thing. 20 feet times 8 feet is going to be 160 square feet. Just because it's slanted, it still covers the same amount of space. This original length is still 20 feet, and it still was moved 8 feet. The difference comes in this third one, even though it's related, that area is going to be 20 feet times 8 feet as well, but it's going to be divided by 2 because it's a triangle. It's only half of that related rectangle. So that's going to be 80 square feet. So now within these, the Pythagorean theorem is going to come up. For example, let's say I have a parallelogram. That doesn't look parallel at all. Let me try that again. No, it's off the other way. Oh, well, pretend that looks like a parallelogram. And if I tell you that this top up here is 30 inches, and that this here is 17 inches down the side, and we find that this piece here is 8 inches. If I want to find the area of that, remember for area, I have to have 2 dimensions that are perpendicular at right angles. So the 30 will work, but I would need to know this distance here, which would be at a right angle to it. To find that distance, I am going to use this right triangle. Within that right triangle, this is a leg, so I'm going to call that A. This is also a leg down here, so the 8 inches I'm going to call B. 17 inches is the hypotenuse, so I'll call that C. So A squared plus B squared equals C squared. Where I'm going to leave A is what I'm looking for. B is 8, so that's going to be 8 squared. And C is 17 squared. Now, I've used these numbers enough tonight. I don't know why I've using the same ones for some reason tonight, but you might be able to predict what A is going to be. 8 is 64. 17 is 289. Now, we'll solve that for A by first subtracting 64. So A squared is 225. And then we'll square root. So A is 15. So up in this figure, A here is 15 inches. So my area, I have 30 inches by 15 inches, which is 450. Remember, we also multiply the names. Inches times inches is inches squared. The perimeter, if I were looking for the perimeter of that parallelogram, would be just adding together the sides. I have 30 plus 17 plus 30 plus another 17, which is going to give us 94 inches of a perimeter. For a right triangle now, let's take a peek. So let's say that this is 9 inches and this is 41 inches. I want you in your notes to see if you can find the area of that right triangle. I'm going to give you a couple minutes. I don't know why lines are disappearing on me. There, I'll give you a couple minutes to find the area and the perimeter. So to do this, we've got to find this dimension right here. I'm going to call that dimension A because it's one of the legs. The 9 is going to be B because that's the other leg. And C will be the 41. So we've got A squared plus B is 9, so that'd be 9 squared equals C is 41, so that'd be 41 squared. A isn't going to change, A squared plus 9 squared is 81. 41 squared is 1,681. We're going to subtract 81 from both sides, solving for A. So we have A squared equals 1,600, and we square root. So again, the square root of A squared is A, square root of 1,600 is 40. A is 40 feet. So up here to find area, which two sides are we going to multiply together for area? 940, there we go. It has to be perpendicular dimensions. So 9 feet times 40 feet, or it could be 40 times 9, will be the same thing. Divided by 2, of course, 180, and of course feet times feet is feet squared. Perimeter, well, 9 feet plus 40 feet plus 41 feet, we just add them together, gives us 90 feet of perimeter. Now I get asked, why isn't that squared or cubed? Because remember, perimeter, we're just adding the sides, and when we add or subtract, we keep the same names. We're a couple minutes early for our break, but let's go ahead and take it anyway. It is 4:18. Let's come back at 4:20. Okay, so our next step is to tie the circles back into this with our area. Now, most of us know the formula for the area of a circle, that the area is pi times the radius squared. So the question I'm going to come up with right now is, where did that come from? So we're going to start out here with a circle with a radius. I'm just going to call it R. So what that means is the diameter of this circle is just going to be 2R. That also is telling us that the circumference of this circle, remember circumference is 2 times is pi times the diameter. Well, it's just going to be 2R is the diameter times pi. It's going to be the circumference. So now what I want to do is I'm going to take half of that circle. So the distance around from here around to there is half of the circumference. If I divide this by 2, well, the 2's cancel out. This distance here is just R times pi, or pi times R. Now, just like we did with that parallelogram where we sliced it into tiny little rectangles, here I'm going to slice this into tiny little slices, but the slices are going to be little pi wedges. And I'm going to slice them as thin as I can possibly get them throughout that whole half circle. Then I'm going to come over here and I'm going to spread them out. I'm going to fan them out. And if I cut them thin enough, what I get is this kind of comb tooth deal. And this up here, they said if I cut them thin enough, is basically a straight line now. Well, now I'm going to do the same thing with the other half of the circle. Now I'm going to cut it into equally thin slices. If I fan out those slices, that should fit perfectly inside the teeth of this other piece I had fanned out. So if I think of cutting those slices thin enough, what I basically have here, This distance is the radius of the circle. That's from the center out to the outside edge. This distance here is r times pi, radius times pi, that half of the circumference. So this forms roughly a rectangle that is an area of r times pi, which is, by a little bit of rearranging, pi times radius squared. You don't need to remember how that formula came out, but I show you that to emphasize the point that all areas come down to a rectangle. Even our triangle, it came down to being just half of a rectangle. Okay, so if I have a circle that has a radius of 4 feet, to find its area, it's going to be pi times 4 squared. So it's pi times 16. If I think of that as 3.14 times 4 squared, or times 16, that comes out to be 50.24. Now the distance on the 4 was feet, so it's feet squared. Is that area, square feet. If I have a circle that has a diameter of 10 inches, finding its area is pi times, is it 10 squared? Say no. Why not? Because 10 is the diameter. We need the radius. So the radius in this would be 5. Very good. Half the diameter. So it's pi times 5 squared. So 3.14 times 25 is roughly 78.5. That's in inches, so it'll be inches squared. Now, before we go any further, I want to talk a little bit about what is an inch squared and what is a foot squared, or a square inch and a square foot, as they're usually called. A square inch is defined to be a square that is 1 inch by 1 inch. That's equal to 1 inch squared. And if you did the math, it actually works out. 1 inch times 1 inch is 1 inch squared. A foot is the same thing. A square foot is obviously not drawn to scale here, by the way. A square that is 1 foot by 1 foot. So 1 foot times 1 foot is 1 foot squared, or 1 square foot. Something that you can note from this, 1 foot is 12 inches. So 1 square foot is 12 inches by 12 inches. Or 144 inches squared. So if I am converting with areas, I have to remember, I'm not going from feet to inches. It's not 12 inches in a foot anymore, because we're not dealing with just feet and inches. We're dealing with square feet and square inches. It is 144 square inches in 1 square foot. So now we can start putting this all together to make some more complex shapes. I'm going to start out with one that looks like this. Let's say that's 20 inches by 16 inches, 12 inches, and 11 inches. Let's say I just want to find the area of this. There are two methods that I can use to find the area of a shape like this. Method one is to cut it up and add the pieces together. What do I mean by that? Well, there's two different ways I can cut this up. I can cut it like this and have two rectangles, 1 and 2. Or I can cut it like this and have two rectangles, 1 and 2. It doesn't matter either way. I'm going to leave it like this. Rectangle 1 is now 16 inches by 11 inches, which is 176 inches squared. Rectangle 2 is 12 inches by, I need to find this dimension up here. What's it going to be? 9, very good. If the whole thing across here is 20 inches and this piece is 11, this leftover piece has to be 9. So that'll be 12 inches times 9 inches, which is 108 inches squared. So that adds up to make 284 inches squared for area. Well, method 2 is to fill in and then subtract. So what that would mean for this one, rather than cutting it into pieces, we would fill it in to make a complete rectangle. And that complete rectangle is 16 by 20. Or 20 by 16, however you want to think about it. That would be 320 inches squared. And then we have to subtract the missing piece here. This missing piece we found, this is 9. What's this dimension here going to be? 4, very good. 16 all the way, this part's 12. 16 minus 12 leaves us with 4. So we are subtracting off an area that is 9 inches by 4 inches, or 36 inches squared. We subtract that out, we get 284 inches squared as our area. So we're going to get the same area either way. And in a problem like this, it's about the same amount of work either way. But there are some problems that are a lot easier to do one way than the other. And there are also problems that must be done one way or the other. Especially when we start throwing in circles, we run into those problems. Like this one. May not have given myself enough room here. Let's see. So what we have here is a rectangle with a half circle on the top, on the side. And let's say that this here is 8 inches. Of course, 8 inches over there as well. And we'll call this across here, oh, let's go with 14 inches. To find the area of this, I have to divide it into pieces and add them together. Piece 1 is a rectangle that is 14 inches by 8 inches, which is 112 square inches. Piece 2 is a half circle. So to do that, the first thing I need is the radius of that circle. What's that radius going to be? 7 inches. Very good. 14 inches across here means it's 14 inches across there. So the diameter is 14 inches, giving us a radius of 7 inches. So that area is pi times 7 squared, but is it a full circle? No, it's a half circle. So we have to divide it by 2. So it's 3.14 times 7 squared divided by 2. 76.93 inches squared. We add those together, we get 188.93 inches squared is the area of that shape. Any questions there? Next. Try that a little bit better. That's a little bit more like a quarter circle. Pretend that's a quarter circle missing out of the corner of this rectangle. We have a rectangle that is 20 feet by 28 feet. This here is 12 feet. Here's an example of one where the only thing we can do is to fill in the missing piece, find the whole area, and subtract out that piece that's missing. So the whole area here is 28 feet by 20 feet. 28 times 20 is 560. Feet times feet is square feet. And then I have to subtract out this quarter circle. Well, first I need to know the radius of that quarter circle. What is this radius here? Well, it'll be the same as this radius here, which is 8. Very good. 20 minus 12 leaves us 8 feet. So that area is pi times 8 squared divided by 2, which is going to be 100.48 square feet that we're subtracting out. So this is going to be 459.52 square feet is the area of that shape. Any questions? Now, based on that example, the actual mathematical name for this shape is called a washer. For those of you that have ever worked with anything mechanical, doing nuts and bolts, you know what a washer is in that context. It's very similar here. What this is basically a ring where on the outside it has a diameter. We're going to say that outside diameter is 20 millimeters. And we're going to say the thickness of this washer here is going to be 8 millimeters. I want to know what the area of the washer is, what the area of this ring is, basically. Think of it as a donut. Well, there are actually two ways to find that area. One way involves a calculus approximation. But the two ways, the main way to find that area is to find the area of the big circle first, which that area is going to be pi times what? Careful. Just 20 squared, right? So pi times 20 squared is going to give us 1,256. Is that correct? That's millimeters, so that's going to be millimeters squared. From that, I need to subtract out the area of this smaller circle. The area of that small circle is going to be pi times, what's that distance? 12. There we go. 20 minus 8 gives us 12 millimeters there. So that's going to be 12 squared. 3.14 times 12 squared. 452.16. And that is millimeters squared. So we subtract there, this is going to be 803.84 millimeters squared is the area of that washer. So what we have here is basically a rectangle that has had both of those top corners rounded off. This rectangle here is going to be 28 inches in this direction. We're going to give, let's do this. Let's say that it is 20 inches in this direction. And we'll call it 22 inches here. To find the area of this one must be chopped into smaller pieces and added together. We have the two half circles, or the two quarter circles, I should say. And then down here, most likely, we're going to cut this across there. So we've got one. I'm going to call this rectangle the second piece. And then 3 and 4 are the two quarter circles. So I'll start out with area 1. That's 28 inches by, what is this dimension here going to be? $18 works. And we get to that because we know if these two quarter circles are identical, those two distances must be identical. The difference between 20 and 28 is 8 inches. Half of that would be 4 inches on each side. So that gives us a radius of 4 inches in each of those quarter circles. So if it's 4 inches that way, it's also 4 inches in this direction, giving us 22 minus 4, or 18 inches here. So yes, that is 28 inches by 18 inches, which is going to give us, what is that, 504 inches squared? Does that look right? Yep, that's right. So that's area 1. Area 2 up here. What are the dimensions of that rectangle? Four inches by 20 inches. Good. It's 4 inches here because that's just the radius of that circle, a quarter circle. And the 20 is given there. So that is 80 inches squared. Three and 4 I'm going to do together. In math, one thing that we're seeing here, one of the tasks is to be able to cut things into smaller pieces. But another thing that simplifies them for us a lot of times is being able to take those smaller pieces and then put them back together again. So here, I have one quarter circle. And I have a second quarter circle. I can take them out of that shape and I can put them together to make a single half circle. This is just a half circle where that circle still has a radius of 4 inches. So rather than finding 2 quarter circles, I can find one half circle. So that's pi times 4 squared divided by 2, which is 25.12 inches squared. So if we add that all up, that gives us a total area of 609.12 inches squared. Time for you guys to try one. That ain't gonna work. We'll just draw. Pretend these lines are parallel. And that those are half circles. And that those are half circles. I'm going to give you this full distance here of 200 feet. I'm going to give you a distance across here of 30 feet. Of course, 30 feet here. And across here, oh, let's call that 40 feet. What I want you to find is basically the area of this track. Not as hard as you would think. It involves all this, many of the things we've already talked about, nothing new. Let's see what you can do. I'm going to give you a couple minutes to work on that. So we're going to cut this across here, cut the half circles off the ends. So we have 2 rectangles here. Each rectangle is 30 feet here by, what's the length here? Did we come up with that? Well, let's step back. What is the radius of this large circle? Let's go one step further back. What's the radius of the small circle? Half the 40 or 20 feet. Good. So if that's 20 feet, we add another 30 to that. The radius of the big circle is 50 feet. So that means from here to here is 50. And from here to here is 50. So this has to be 200 minus 50 and minus another 50, 100 feet. So that's 30 feet by 100 feet, which is 3,000 square feet. And there's another one down here. It's the same size. Now, next we have to look at these shapes over here. The ends. If I take those and put them together, I have basically a washer just like we did before. The big circle has a radius of 50 feet. And the little circle has a radius of 20 feet. So that area be pi times 50 squared is the big circle. So 3.14 times 50 squared. 7850. So 7,850 square feet. The little circle is pi times 20 squared, which is 1,256 square feet. We subtract there to get a difference of 6,594 square feet. So that is this piece here plus this piece here. So that adds up to 12,594 square feet of total area. Show of hands, anybody get that? One person, a couple of you are close, that's not bad. Finding the circles, okay. That's a tough problem. You know, having seen it once, that makes it a little bit easier. We may revisit that at some point in the future. For now, there is a new quiz that will be due tomorrow, Wednesday, at 11:59 p.m. And there will be a new homework that is due for Thursday. You guys have a great night. I'll be here till 5:20 if you want to work on any of that and have any questions.